Today, we are diving into a really major breakthrough in AI. Seriously, researchers have just managed to crack a puzzle that could make artificial intelligence learn smarter and way, way faster than we ever thought possible. So let's get into how they pulled it off and what it could mean for our most advanced AI systems. So here's how we're going to break this whole thing down. First up, we'll tackle the big efficiency puzzle that's been holding AI back. Then we're going to look at the main culprit, something called the exploration trap. After that, we'll see the one clue that changed everything, explain the new map first, then conquer strategy, and finally wrap it all up with what this means for building smarter AI faster.
All right, let's dive right in. You see, for years, AI researchers have been wrestling with this fundamental problem, a huge gap between what an AI should be able to do on paper and what we can actually get it to do in practice.
This right here, this is the core of it. It's not really a question of if an AI can eventually figure out how to master a task. I mean, we've all seen AIs do incredible things. The real question is, can it get there without taking an eternity and using an insane amount of computing power? Can the learning process itself actually be efficient?
The specific area we're talking about is called reinforcement learning, or RL. This is the magic behind AIs that master super complex games, control robots, and yeah, even fine-tune the big language models we're all using. The AI, or the agent, basically just tries a bunch of stuff, sees what gets it a reward, and over time, it learns the best way to do things. It's trial and error, just on a massive scale.
Now, to zero in on the problem, researchers looked at a very specific condition. It's called linear Bellman completeness. I know, it's a mouthful. But all you need to know is that it describes a type of problem with a really clean, predictable structure. And in theory, if a problem has this structure, an AI should be able to solve it efficiently, no sweat.
And that leads us smack into the puzzle itself, what everyone in the field calls the statistical-computational gap. We had the math that proved a solution could be found efficiently, but for years, nobody could actually write an algorithm that a computer could run efficiently to find it. It was this incredibly frustrating disconnect between what we knew was possible and what we could actually do.
So why? Why does this gap even exist? What makes the problem that's theoretically pretty straightforward so incredibly hard to solve in the real world? Well, it all comes down to one massive challenge.
The big bad here is exploration. Think about it. For an AI to learn the best way to do something, it has to explore its world first, to see what's even out there. But how is it supposed to do that? If it just wanders around randomly, it could take, practically forever to figure things out. It gets stuck in this exploration trap. People have tried to crack this nut before, of course, but the old methods basically fell into two categories. One approach, using optimistic bonuses, was kind of clever, but it was too messy. It ended up breaking that nice, clean structure we just talked about. The other approach, called version spaces, kept the structure but was too slow, a total computational nightmare. So neither one was a real solution. So to finally solve this, researchers needed a new angle, a fresh clue, and they found it by narrowing their focus. Instead of trying to solve every problem at once, they decided to look at a very specific but really important type of learning environment. And here's the breakthrough. They focused on worlds with what are called deterministic transitions. Just think of a simple video game. If your character is in a specific spot and you hit the right button, it always moves one square to the right. The outcome of your action is totally predictable. The physics of the world are set in stone. Now, the rewards you get might still be random, but just knowing for sure where you'll end up after an action, well, that turned out to be a massive clue.
Now, even with this simplification, this was still a really hard, unsolved problem. But by focusing on these predictable physics, researchers finally got the foothold they needed. It was the key that let them build a whole new kind of algorithm from the ground up. And that one clue led them to an incredibly elegant two-part strategy, a new master plan for the AI that neatly dodges all of those old problems.
The strategy is it's beautiful in its simplicity. Step 1, exploration. The AI's only job is to go out and methodically build a reliable map of its world. This map is called a policy cover. Step 2, exploitation. Only after the map is completely finished does the AI use it to figure out the single best path to get the biggest reward. So what is this map, this policy cover, exactly? Well, it's not like a picture. It's more like a curated set of GPS routes, a small collection of pre-planned paths.
And together, these paths guarantee that the AI can get to every important part of its environment and see what rewards are there. It completely replaces random wandering with a super structured way of gathering intel.
And you see how this works, right? By cleanly separating the job of mapping the world from the job of finding the best path, this whole strategy just sidesteps the old traps. It's not too messy because the exploration is highly structured, and it's not too slow because all the hard planning work only happens one time, right at the end, after all the information is in. Okay, this is all fantastic in theory, but let's bring it back to the real world. Why does solving this very theoretical problem actually matter for the future of AI? What's the bottom line?
A bottom line is this. We now have the first truly efficient algorithm for this whole class of problems. The technical term is polynomial complexity, which is just a fancy way of saying it's actually practical to run on a computer. It means that as problems get bigger, the time it takes to solve them grows at a reasonable, manageable rate, not an impossible one. And this isn't just a small improvement. This is a big deal. It provides a real, concrete answer to a fundamental question that the entire reinforcement learning community has been wrestling with for years. It's like they've finally closed a major chapter in the story of AI. And this is where it gets really, really exciting. The authors of the paper point out that fine-tuning large language models, the brains behind tools like ChatGPT, has a key feature in common with their problem, those deterministic transitions. When a language model writes the next word, that choice is determined by the prompt and the words it's already written. Because of that structural similarity, this new super efficient algorithm could be the key to training our most powerful AIs much, much faster. So, as we wrap up, we're left with a pretty powerful idea. By finally solving one of these huge, long-standing roadblocks in how AI learns, we haven't just found one solution. We've developed brand new tools and a whole new way of thinking that could help us start taking on the next set of impossible challenges in AI. The door to what's next is officially open.